Okay, thank you very much. So thank you to Nina and Juan for chairing the session, the organisers for inviting me. So I'm talking about hydrolyzed protein use in preterm babies. I'm going to start off with an overview about protein intakes in general, with some concepts, and then talk a little bit more about hydrolyzed proteins. I've got some conflicts that you can read here from industry who've sponsored some of our research. But we have a website, and I put all the slides from the talk today. So if you have a smartphone and you shine it at that QR code, it will take you to the slides today. So rather than having to take photos of all my slides, you can just download them for free. And an important point to make is that I'm a clinician. I'm not a food scientist. I don't understand some of the industrial complexities of hydrolyzed proteins, but I'll give you my take on them. So the full version of the talk is I'm going to talk about nutrient needs and brain growth, a concept of nutrition that I've been kind of developing, a bit about protein breakdown and hydrolysis. There's a summary version here if you want to go to sleep, because you can just look at the slides later on. So the summary version is protein is important. There are no data to show hydrolyzed protein formula improve outcomes, and that's the end. So if you want to go to another talk, you can do now, because that's basically the bit. This diagram really emphasizes the importance of brain growth in our preterm babies. So unlike most primates, the rapid period of brain growth in humans takes place in the third trimester and immediately after delivery. So that between 24 weeks and 2 years of age, we acquire about 90% of our final adult brain volume. And nutrient needs in preterm babies are massive. This is Egan Bernal, who is a Colombian rider who won the Tour de France this year. He cycles up and down mountains for a living, and during the Tour de France he consumes about 7,000 kilocalories a day, and he's still really thin. So just think how fantastic it is to be able to eat that much calories but still stay thin. So his caloric requirement is about 20 or 30% less than that of a preterm baby, where we know they need at least 120 to 130 kilocalories a day. And remember that over half of that energy expenditure takes place in the brain. And importantly also, protein requirements in preterm babies are massive. So we estimate that enteral protein requirements are around about 4 grams a kilo a day, and that would be roughly equivalent to us eating about 12 or 15 beef burgers every day. That's how much you would need to eat to meet the protein requirements of a preterm baby. So protein is essential for lean mass accretion. What is lean mass accretion? Basically everything in the body that isn't fat or water is lean mass. Your bones, your blood, but importantly your brain. And therefore insufficient protein may adversely affect the development of all these different organs in terms of their size and structure. And in humans it's all about the brain. We know that in animals they actually have very small brains compared to head size, whereas in humans the brain fills the entire cranial cavity. And when you map out brain size against body size mapped out here, you can see that the human brain is about 10 or 20% as big as every other species, and that rapid period of brain growth happens in the third trimester and after delivery, and therefore protein in this period is particularly important to babies. And brain growth is of course not just size. There's lots of different processes happening. These are all under control of various growth factors, and particularly IGF-1, and there's some great studies on this, and there's a talk on this yesterday. And your levels of IGF-1 are directly related to the macronutrient intakes you have, but of course a whole range of other factors that determine levels of growth factors. And all of this complexity of brain development has to take place in all these different anatomic regions, and you have to do it in sequence. And if you miss out one of the steps, you can't go back and do it again. And that's why it's very important that you meet your macronutrient needs right from the beginning. And there's been a lot of studies. Most of these are observational. This is one of our favourite studies. This is now about 10 years old. And what it shows you is that for every extra 10 kilocalories a kilo of energy intake in the first week of life, MDI is about 4.6 higher at 18 months of age. And for protein, for every extra gram, it's about 8 MDI points. But this is observational data, and the controlled trials have struggled to really show such a key impact. So what is nutrition? So nutrition, it's very important to understand, is more than nutrients. So though we talk a lot about the proteins, the fats and the micronutrients, nutrients are just one aspect for me of nutrition. Of course there are these key functional components, particularly important in breast milk, HMOs, growth factors, enzymes. The next component for me is now the influence of microbes in the gut. These are determined by breast milk exposures, but also the other environments, probiotics, these things. And then there are the kind of technical and socio-behavioural aspects, how you feed a baby, taste, sensation, these things. So we can think about this, the same kind of concept for protein. When we think about protein, from the nutrient point of view, we're thinking about protein quality and quantity and the amino acids, but also the functional components in relation to this talk. That's the peptides that are produced by protein breakdown that influence gut-brain activity. The microbes that may be differentially affected by hydrolyzed peptides, lactoferrin, alpha-lactalpha.
Sorry, excuse me, Nick. Please come to the front. There are seats at the front here.
Yeah. So microbes affected by different kind of breakdown products of protein. And then, of course, with hydrolyzed proteins, there may be aspects of solubility and taste, but also osmolality and all these things. So those, for me, are the four components of nutrition when you're thinking about how to assess the data. But of course, in preterm babies, it's difficult to assess protein nutrition status. If I sent one of my fellows to assess the protein status of this baby, they would struggle. In fact, if I asked them to go and assess nutritional status, they look at me like I've asked them to do something strange. Nobody really understands how to assess nutritional status. And if I stand there long enough, they might get out a tape measure, and if I'm really lucky, they might plot it on a growth chart. But actually, we struggle to understand how we should assess protein needs or protein status in our babies. And when I was a trainee, I thought, like lots of my fellows, that there must be some blood test. And you can just do a blood test, and you put it in a little bottle, and you send it to the lab, and you say, oh, can you, this is a premature baby, 26 weeks, protein status, and then you write please underneath, and you underline it, and then the lab is going to do these analyses that tell you whether the protein status is good or not. And of course, nothing like that exists. But that's what you think when you're younger, that somehow there's going to be a blood test that will solve this. So this is very old data, body composition of the reference fetus. And this is how we've used this sort of model to estimate protein needs and energy needs in babies. What's important to see here is that babies at 24, 25 weeks gestation are between about 80 and 90% water. So a 500 gram 24-week baby really only has about 50 grams of dry tissue that we're dealing with. And fetal accretion is about 2 grams a kilo a day. And therefore you're going to need much more than 2 grams a kilo a day because of all your losses of nitrogen in the stool and in the urine. And we can put all this data together, add in some factor for inefficiency, and come up with this sort of model. This is all based on Eckhart Ziegler's work from 30, 40 years ago. We can put these things together, predict them over the third trimester, and you can see using this type of model, you can guess that protein requirements are going to be around about 3.5 to 4 grams a kilo a day. A bit higher in the very small babies, perhaps a bit lower after 30 to 32 weeks. So that's one of the models that we've used to estimate requirements. But remember that all the babies you're looking after are very different. So here are 2 babies weighing 600 grams. One's a 23-weeker, one's a 28-weeker. They're both 3 days old. Clearly those babies are very different nutritionally in terms of the vulnerability. Here are 2 babies weighing 1,700 grams. One's a 33-weeker who's only 3 days old. The other's a 23-weeker who's 80 days old. So you have to remember that when you're dealing with all these recommendations, that you need to use these recommendations to guide practice, but they do not dictate the right thing in every baby in front of you. So we developed some concepts about protein intake, the idea that there is a sort of linear relationship as you increase, but there comes a break point beyond which more protein is not going to be helpful. So above this break point here, giving more protein isn't going to help the baby, and indeed giving excess protein might be harmful metabolically. The next concept is that you might find that you optimize brain outcomes at a slightly lower level of protein intake than, for example, length gain or measures of nitrogen retention. So it depends what outcome you're using in terms of what you think is the optimal amount of protein intake. And of course you need plenty of energy. If you don't give enough energy, you won't be able to accrete the protein that you're giving. The amino acids are just going to be catabolized. So too little protein is harmful. Too much protein, as we've heard over the last couple of days, may also be harmful. In the short term, you may have high peaks of amino acids, or you may interfere with protein breakdown or autophagy. And in the long term, excess protein might drive IGF-1 and obesity. And although there have been several trials in preterm babies, most of the data is underpowered to look at brain outcomes. So my feeling is that you should be giving at least 3.5 grams a kilo a day every day of that baby's life. You should include, of course, parenteral and enteral sources. But for me, if you're feeding enterally, I would recommend that you aim at least 4 grams throughout the majority of their NICU stay. And I would say that lower intakes risk maybe not meeting your essential amino acid requirements. So, protein is a driving source for growth. It's the major functional and structural component of all the cells in your body. In the absence of data to the contrary, I think you should take care if you intend to regularly give less than these amounts. Now, I didn't do chemistry at school, but I always thought, wouldn't it be wonderful if we could just use all the nitrogen that we're breathing in, all the air around us, and every day you put the baby on a ventilator and you pump nitrogen into them. And wouldn't it be wonderful if you could just turn that into amino acids? But of course, as animals, we must get our amino acids from the diet, and that's either enteral protein or parenteral amino acids. So this is Protein 101, the basics of protein digestion. Just going to talk you through what hydrolysis is. Of course, we should just feed mother's breast milk if we have it, but if we haven't got breast milk, should we use a hydrolyzed milk? So protein, as you know, is made up of amino acids, and this is the structure of amino acid. I drew it out because I didn't do chemistry at school and I thought it'd be interesting to understand. And here we are, you can see that you have 2 hydrogens bonded to a nitrogen, which is your amino group. You have your carboxyl group at the end, and then you have this carbon backbone with a side chain that determines the specific type of amino acid. That's called the R group on the side. So the R group will be different between the different amino acids. So whilst we eat protein, what we tend to measure in the metabolic studies is nitrogen, particularly nitrogen loss in the urine. But really what we need are amino acids. And all of you know that we need essential amino acids because we can't make these themselves. We also need a source of other nitrogen amino groups. But in preterm babies, there are these conditionally essential amino acids that may be important, particularly in preterm babies. So there are 9 essential amino acids. You can look them up in the book. I can never remember them. 6 conditionally essential amino acids. And so all of these probably have to be supplied in the diet for a preterm baby. So this is what protein looks like. I think this is important to understand what we mean when we're talking about hydrolyzed proteins. So you have the basic polypeptide chain, which is all your amino acids stacked together, hundreds of them all stacked together. And then this forms into a helix or a sheet, and that's the secondary structure of protein. Then there's a tertiary structure where these sheets get folded up, and then a quaternary structure which goes to form the kind of globular proteins and the membrane proteins in our body. And hemoglobin is a great example of that. And you need that quaternary structure for the functional activity. So if you take your hemoglobin protein and you unfold it, it won't work, it won't be able to carry oxygen. So that quaternary structure is very important for functional activity. So this folding is key, and this folding is held together by hydrogen bonds that are actually quite weak. And when you hear about proteins being denatured, what you're really saying is that they've lost their structure. The amino acids are all there, but the complex structure has started to fall apart. And that happens under the influence of acid or heat, or maybe osmolar stress. And when you lose that quaternary structure, you then lose the function of that protein. And here's a great example. I didn't have an egg for breakfast, but many of you will have had an egg. It starts off with this sort of looking like this, but of course as soon as you cook it, you start to denature it, and it kind of changes structure. The amino acid composition is exactly the same, but you can't put it back into its primary quaternary structure again. You've irreversibly changed it. And it's a bit like putting, this is a great analogy, putting paper clips in a bowl. And once they've joined together in that structure and been denatured, you kind of can't unfold them back to where they are. So this is what hydrolysis is doing. It's breaking down these complex structures. So as I say, protein needs are very important, amino acids are very important, and there may be subtle differences in amino acid requirements in very preterm babies. But the concept is much more complex than just working out how many amino acids a babies need. Because we know that lots of these proteins have functional activity. So IgA and lactoferrin, as you know, you can detect some of these proteins in the stool. The whey peptides, so lactoferrin broken down into lactoferritin, has immune activity. But also the casein element of your milk is broken down into other peptides, casomorphines, casein phosphopeptides, They're important for mineral absorption and may be important in regulating the gut-brain axis. So what is the gut-brain axis, and why might this be important in protein hydrolysis? Well, the gut-brain axis describes this interaction between what's happening in the gut and what's happening in the brain, and it's a big area of research at the minute. I'm not sure how relevant it is to preterm babies, but you'll find a lot of papers on it in the adult literature. And the idea is that we have all these communities of gut bacteria that are being influenced by the nutrients in your gut, but in turn also producing a whole range of metabolites. And all of these metabolites are then interacting with the central nervous system, and some of this is modulated by the enteric nervous system. And there's a lot of data in adults to show that the pattern of gut bacteria and the gut-brain axis influences things like your bowel habit. You might be interested to know that people with Parkinson's disease have a history of constipation many years before they develop the symptoms of Parkinson's disease. So something very profound and interesting about what's happening in the gut and how this influences the brain. And as I say, whilst that might be not of huge immediate relevance to preterm babies, maybe some of these peptides are modulating intestinal activity, motility, and all these types of things. And as I say, there are lots of mechanisms that link the gut to the brain, but some of these will be the peptides that are broken down from the food that you're eating. So when we think about protein digestion, there are very few studies, lots of factors. It isn't just the proteases, it's all about your stomach pH and motility. And breast milk itself contains proteases and antiproteases, and lots of your bacteria are also involved in protein breakdown. And if you don't break your protein down effectively, there may be advantages and disadvantages. You may lose some proteins and peptides with functional activity. We know that some of these proteins and peptides may be involved in allergy. There's some suggestion that some of these products might be involved in sleep behavior, certainly mineral absorption. And also, if you don't break your protein down effectively and it passes through to the distal ileum and colon, your protein is then fermented and produces all these amines and phenols and sulfides that may be toxic to you and may be injurious to the gut and result in neck or something like this. So human milk itself isn't whole protein. There are lots of different subunits there, the caseins and the whey fragments. And actually, when they've looked at it, you see more hydrolysis in milk coming from a mum delivering prematurely compared to a term. And proteases in milk initiate some of the digestion that's going on. And there's probably also proteases in our saliva. So again, here's the simple thing. We know that all of us sitting in this room have quite an acid pH in the stomach. In preterm babies, it's not really quite so acid, so the protein digestion is different in very premature babies. But then we have these proteases in the brush border that help to break things down. We have bacteria, particularly propionibacteria and Bacteroidetes, that are involved in proteolizing the peptide links. And then, as I say, protein that reaches further down is probably fermented by anaerobes. And I've drawn out here the sort of mechanisms by which you start with whole protein and go to the bottom. So effectively, we disrupt this quaternary structure into the peptides and into amino acids so that we can absorb them. So the actual protein structure of breast milk is very complex. As you know, you have these caseins, particularly beta-casein, very critical for calcium absorption. The whey proteins, particularly alpha-lactalbumin and lactoferrin, involved in immunity. The mucin proteins that I'm not talking about. But remember that human milk evolved over millennia and evolved to be primarily a whole protein milk. So hydrolyzed proteins do exist in nature, but most of what babies consume is whole protein. And knowing that preterm babies kind of struggle with their gut, it might be logical to say, why don't you help them along a bit and just give them some hydrolyzed protein in their formula? So of course we always promote mum's breast milk, but what do we do if there isn't enough? Should we be using a hydrolyzed protein? So there are lots, as you know, commercially available formula. I'm not going to be talking about any of them. It's not clear to me why so many of the currently available preterm formulas are already partially hydrolyzed. I don't know what started it off, whether people were worried about allergy or digestion. But if you go back to your units and look at your preterm formula, you might find that some of these are partially hydrolyzed. Extensively hydrolyzed formula available. We know that the pediatric surgeons love them. I'm not sure there's a lot of good data. They have higher osmolality, and most of these have been formulated for term babies, and so they won't meet your nutrient needs. Partial and extensive, there isn't really an official definition, but generally extensively hydrolyzed formula have many, many more peptides that are less than 3 kilodaltons, but don't really worry about how these differences are. Important to be aware that there are differences between the US and Europe. If you want to call a formula hypoallergenic in the US, you have to have studies that show the majority of your patients get better. But I don't think for me there's any strong evidence that calmic allergy type issues are relevant in preterm babies. So in a commercial sense, they use industrial proteases, but also enzymes. I think some of these still come from pig sources. And they break the proteins down, but the process of breaking it down in the factory is very different to what would be happening in a preterm baby's gut. The end product is then going to vary between all the different companies out there, and they'll be different now to what they were 20, 30 years ago because they've changed the composition. So some of your bioactive peptides that you think might need to be there for the gut-brain may be absent. You may also create peptides that wouldn't naturally exist, and we don't yet know whether these have any functional activity. And you may also increase free amino acids. So what's the evidence base for use in preterm babies? Well, we did a Cochrane review on this using standard methodology comparing hydrolyzed proteins to standard where the primary outcome was looking at feed intolerance or NEC. It's a very short story. There are very few studies. There's absolutely no data really to show convincingly that hydrolyzed proteins affect feed tolerance or affect the risk of NEC. And here's the data more starkly. So in feed intolerance, only measured in 3 trials, a total of 161 babies in the world literature from good controlled trials. And for NEC, only 5 trials with 385 babies. No trial less than 1,000 will ever really tell you whether your intervention reduces your risk of NEC. You do see slightly slower weight gain, probably because of the nitrogen quality, but we concluded that out of 11 small RCTs, there's no consistent evidence of benefit in the trials that have been done so far. You also see different amino acid profiles in babies fed hydrolyzed milks, not surprisingly. Not clear whether that's functionally relevant. There's a little bit of data, but virtually nothing on mineral absorption, but this is going to be different. The reason you have casein in milk, and the reason why milk is white, is because the casein holds onto the calcium. It's not the fat that makes milk white, it's the casein and the calcium. Nitrogen retention is less good with hydrolyzed milks. It used to be a lot worse, but now it's probably only 5 or 10% less efficient. But that gets worse the more you hydrolyze it. But there's virtually no data on insulin or IGF-1 pathways, despite the fact that you're feeding these babies with more potentially branched-chain amino acids. You get more rapid amino acid absorption. There's virtually no data on maturation of the GI tract. No data on whether these peptides are doing anything. No data on maturation of pancreatic function, yet some evidence suggests you need whole protein to mature pancreatic function normally. No data on what this is doing to the microbiome, and a little bit of observational data from this study, I think in Holland, that showed a higher incidence of vitamin K deficiency in babies receiving extensively hydrolyzed milks. So I think there's enough there to suggest that hydrolyzed proteins may cause harm. They might be beneficial, but they may also be harmful. And the free amino acids that are produced more quickly may potentially exceed protein capacity. More likely they just get catabolized. But you do see higher urinary excretion of amino acids. And again, whey protein hydrolysates will be more rapidly absorbed, and we don't really know what that does to the baby. We know it's likely to affect gastric emptying. Also, hydrolyzed proteins are going to be more expensive than standard formula. There are differences in taste. I don't know if any of you have tasted these hydrolyzed milks. They taste pretty disgusting. Maybe that makes the babies more tolerant of food when they're older. Maybe it's a good thing. But let's say virtually no data on metabolic, endocrine, microbiomic or cognitive outcomes. So remember that when we're talking about protein and needing so many grams of this, we really need to understand about protein quality. Here are 3 fluids. They've all got 1 gram of protein. One is a bag of PN, one is formula milk, and one is breast milk. They're nothing like each other, but they all contain 1 gram of protein. But the levels of functional proteins, peptides and growth factors may be vastly different. So in summary, protein needs in preterm infants are very high. Amino acids and peptides may differ in very preterm babies. Human breast milk is very complex, all these peptides and proteases already in breast milk, and this has evolved over millennia. And the composition of breast milk, being primarily whole protein with that balance of casein and whey, is there for a reason. Hydrolyzed proteins may be beneficial in certain situations. I've yet to find the studies, but as I say, we have to be sceptical about whether routinely using hydrolyzed proteins is necessarily the best thing. And I would challenge all of you, is it acceptable that we know virtually nothing about the impacts of what we feed our most vulnerable babies? It is slightly outrageous that there are only 161 babies in the trials over 30 years. We know nothing about what this is doing to the babies. I'm not saying hydrolyzed proteins are bad. I use them. They might be good in certain situations, but we should be much more skeptical. And you should all help do more research. So here's my summary. You need to do more research on this thing. You could set up a whole load of great studies comparing a hydrolyzed protein to a whole protein and measure differences on the microbiome. Be very skeptical of what the so-called experts are telling you. We're just like you. We're just clinicians like you. We might be getting it wrong. You can go to the website and download the slides there. And this is what one of my wise older colleagues told me once. He said, Nick, an expert is someone from another hospital who brings PowerPoint slides. And that's virtually all I am, and I'll finish there. Thank you.